So in continuation of the code conversion program, today we will be discussing the program which will be used for conversion from the binary number to the ASCII code. And later on, we will also discuss how to convert the ASCII into the binary. Now, as far as the ASCII codes are concerned, which is American Standard Code for Information Interchange. In the short form, it is known as ASCII, that is ASCII. And the common implementation of this ASCII code is used in code communication, data communication. And what is this ASCII code? It is a 7-bit code. And it's 128 combinations. Since it is a 7-bit code, so 2 to the power 7. So there will be 128 combinations. And these combinations are assigned to the different alphanumeric characters, right from every numerals from 0 to 9, as well as the English alphabets from A to Z. Along with that, some more symbols which are used for the communication purpose. So normally in the ASCII code, the decimal numbers from 0 to 9, they are being represented as 30 and 39 respectively. It means 0 is represented as 30, 30. 1 is represented as 31. 2 is represented as 32. 3 is represented as 33, and so on. And the letters, the English alphabets from A to Z are represented by 41 hexadecimal to 5A. For example, A is represented by 41 hexadecimal number, B is represented by 42, C is represented by 43, and similarly Z is represented by 5A. So it means if we have any number which has to be converted into an ASCII code, and if it is a numeral that is from 0 to 9, so if we add 30 in 0, so 30H will be the ASCII code. It means if we have to convert a number into an ASCII code, and if that number is a numeric, then in that case, we can add 30 and can get the ASCII corresponding to that numeric. So if it is from 0 to 9, very simple way to convert it into the ASCII by adding 30. And if there are English alphabets from A to Z in capital letters, then we can obtain A to Z by adding 37 in that. Since A represents 10, and 10 when it is converted into binary, and if we add 37, we will get 41H. So if numeric are there, we have to add 30. And if alphabets are there, we will add 37. So there is a difference of addition from 30 to 37. If the numeric value has to be converted, we add 30. But if A to Z characters have to be converted into ASCII code, we have to add 37. It means we have to add 7 into that. And for this conversion process, we have to write a program, and that program will be known as binary to ASCII code conversion program. Suppose we have 5 numbers which has to be converted, and these numbers are available in the different memory location from 2000 to 2004 as the numbers are 1, 2, 9, A and B. And after converting 1 to 9 AB, it has to be stored at a certain memory location starting from 2200. And the result should be 1 to 31, 2, 32, 9, 39, A, 41, B, 42. And how this conversion will be done? By adding 30 if it is a numeric, by adding 37 hexadecimal if it is an alphabet. So with this process, we are going to write the program. This is the program for the conversion of ASCII code binary to ASCII. And this program will be using subroutine for the conversion process. So let us understand the individual line one by one, how this conversion is to be done. So first of all, since we are using subroutine, so we have to subroutine automatically uses stack pointer, stack locations. So for that, we have to initialize the stack pointer. So suppose the stack pointer is initialized by the highest memory location, that is 27FF. So with this instruction, 27FF will be stored in the stack pointer. The next instruction is to load the source memory pointer where the datas are written. Suppose the numbers which has to be stored is available at 0850, 0851, 0852, 0853, and so on. And we have to store the converted number at the location from 0860 onwards. Now these memory locations could be anything. It depends that how you are going to define the where you have defined the input and where you want to store the output. So this is varying in nature depending upon the programmer's availability. Now 5 numbers has to be converted. So we have to initialize the counter, and suppose for that purpose, we are using C register to initialize the counter. We have to convert 5 numbers that I have explained earlier, 1, 2, 9, A and B. So we have initialized the C register, which is working as a counter as 05. Now we have to start the process by reading the number, storing the number into the accumulator. So the first number which is available at 0850 will be copied in the accumulator. So the first number, suppose the first number is 01. Suppose the first number is 01. So we have to adopt a process in which we have 01. So 0 has to be taken separately, 1 has to be taken separately, and then we are going to do the addition process. So once we store the number into the accumulator, temporarily we save that number in the B register also for the later use, because we have to separate 0 and 1. So one by one we will be separating. So first of all, what we are going to do, we are going to make the shifting operation on the right hand side. And the purpose is whatever is the higher byte, shift that higher byte to the lower byte side and the lower byte to the higher byte side. And for that purpose, we have to shift 4 times the content of the accumulator, which is the first number. So first number is rotated right. So the D0 bit will become D7 bit. And D7 bit will become D6 bit, D6 bit will become D5, and so on. And we execute this process 4 times so that the higher order nibble, you know, nibble is a 4 digit. So if an 8-digit number is there, so we have two nibbles in that. One is called higher order nibble and another is called lower order nibble. And by doing RRC instruction, by executing RRC instruction, we are able to convert the lower order nibble to the higher order nibble, and higher order nibble will become the lower order nibble. And once this process is over, it is required to extract the higher order nibble first, which is shifted to the lower order nibble. So for that purpose, we are using subroutine, and the name of the subroutine is ASCII. So we are going to call the ASCII subroutine. So it is called by name. Of course, whenever we are feeding this program into the memory location, this ASCII will be replaced by that memory location where the subroutine has to be written. So when we are doing call ASCII instruction, it will call the ASCII and it will come over here instead of executing the rest. So when call ASCII, it is going to call subroutine named as ASCII. And what is it is going to do? It is going to mask the higher order nibble. Once you have shifted the lower order nibble into the position of higher order nibble, and higher order nibble has become the lower order nibble. So the first step is to mask the higher order nibble. And for that purpose, we are doing AND operation with 0F. So what will happen? Whatever is the higher order nibble, that will become 0. And whatever is the lower order nibble, that will remain as it is, whatever its value is, because it is being ANDed with 0, 0, 0, 0, and 1, 1, 1, 1. So because of the property of the AND operation, we are going to mask the higher order nibble and the lower order nibble will remain as it is. Then we try to check, once we are doing that, whatever we have got in the form of a lower order nibble, after doing ANI 0F, we are going to compare that whether this number is less than 10 decimal, whether this number lies in between 0 to 9, or it is more than 9. And for that purpose, we are using compare instruction immediately with 0A. If the number which is available in the lower order nibble is more than 9, then carry will not be generated. But if the number which is available in the accumulator, which is the lower order nibble, if it is less than 9, then the carry will be generated. So when the carry is generated, it means the number is in between 0 to 9 because we are comparing with 10 and carry is generated. It means the number is lying in between 0 to 9. So what we'll do, it will jump on carry next. So carry will be generated and it will come to the next. And in the next, 30 will be added into that. So that if the number is 1, it will become 31. If the number is 2, it will become 32. If the number is 3, it will become 33. But suppose the number which is available in the accumulator in the lower order nibble is more than 9. Suppose it is A. That is more than 9, that is 10. Then in that case, carry will not be generated. So if carry is not generated, instead of going to the next, it will go to ADI 07. So first it will add 07, then it will add 30, and then it will return. So depending upon the value which is available in the lower order nibble, we are going to add either 30 only, or we are going to add 7 and then 30. It means if the number is more than 9, we have to add 37. So for that, first 7 is added and then 30 is added. But if the number is lying in between 0 to 9, so only 30 will be added and it will return. So whenever it will return, where it will return? It will return to the main program from where it has left, just below that instruction, which is used as a call instruction. So when it is going to return, it will return to Stxd. And what is the meaning of Stxd? Is to store the content of accumulator into the memory location whose address is given by DE pair. And what is DE pair? DE pair is showing destination memory pointer where we have to write the result. So first of all, 0, 1 has been converted, and then 1 is converted, and then the result is stored in the form of a 31, which is 31 is available in the accumulator, and it is stored at the location 0860. So 0850 was containing 1, and after calling and executing the subprogram, 30 has been added, and 30 after adding 30 accumulator will become 31, and this 31 is stored at the memory location 0860 by using Stxd instruction. And then we increment the D pair content by 1 so that it will become 0861. Now, out of this value 0, 1, only 0 you have converted, you have not converted 1. So what will happen? Again, we are taking the B value, which we have saved as the byte back into the accumulator. And then we call the ASCII. Again, we call this. Now, whenever this is going to call, it is again going to mask the upper higher order nibble so that we will be having only the lower order nibble. Only lower order nibble will be checked now, whether it is less than 9 or not. If it is less than 9, we add 30. But if it is more than 9, we add 7, and then we add 30, and it will return. And when it will return, now it will not return to this Stxd, but it will return to this Stxd because this call instruction has been executed. Once it reaches here, it is going to store the content of the result, which is stored in the accumulator in 0861. So 0860 contains the ASCII code of the higher order nibble, and 0861 will store the ASCII code of lower order nibble. And once it is done, we increment the content of HL pair. HL pair was previously 0850, now it will become 0851. And after doing that, since 1 byte has been converted, we again going to decrement the content of C, that is the pointer, that is the counter. So it was previously 5, now it will become 4. Since it has become 4, it has not become 0, so it will go back, jump on no 0 back, it will go back to the move AM. Now move AM will trying to get the second number, that is 0851 content into the accumulator. And the same process is repeated. First of all, that number is stored temporarily in the B register. Then we do right shifting 4 times. After shifting it right 4 times, we call the instruction, which is ANI 0F, which is going to mask the higher order nibble, so that we will left with lower order nibble, which was actually the higher order nibble. We try to check whether it is less than 9 or not. If it is less than 9, we add only 30. But if it is more than 9, we add 7 and 30, and then it will return. When it will return, it will come over here. It will store the content at 0862. That is the content of the higher order nibble converted into the ASCII code. And then we increment the content of D, that is D pair is being incremented so that it will become 80863. And then we call to get the lower order nibble. First of all, higher order nibble is masked so that, and then checked whether it is less than 10 or not. If it is so, then we add 30, otherwise we add 7 and then 30, and then it will return. When it will return, it will come to here and it will store the content at 0863. And then we will increment the content of HL pair because 2 bytes have been converted. Decrement C, so 5 will become 3, 4 will become 3, and it will not 0, so it will go back. And in this way, this problem is going to till the counter becomes 0. When the counter will become 0, it will not go back. It will come to the halt and the program will stop. So in this way, the conversion program from the binary number to the ASCII number can be done with the help of two subroutines. So let us go with the algorithm which we have used. First of all, we are going to transfer the byte into the accumulator and then separating the two nibbles. Suppose we have the byte is as 9F. So converting this 9F as 09 and then 0F. And then we are calling the subroutine to convert each nibble into its ASCII hex code. That is 09 will become 39, 0F will become by adding 37. And then we are going to store the code, that is ASCII code, in the memory location 0860 and 0861. So actually what we are going to do, the main program is transferring the binary data into the accumulator, and then it is shifting the higher order nibble into the lower order nibble place. Then we are calling the conversion subroutine and storing the converted value into the memory. Then it again retrieves the same byte again and repeats this conversion process for the lower order nibble. And after the lower order nibble and the higher order nibble is being converted into the ASCII code, it is being stored in a certain memory location. So in this particular program, the masking operation which is being done, we are using one time only. That is, ANI is used once in a subroutine rather than twice, because one ANI is being used for a lower order nibble and second ANI is being used for the higher order nibble. So in this way, the binary to ASCII code conversion program used to work. Now the next one is the ASCII to the binary conversion. Now ASCII to binary conversion is a just reverse process. It is a counterpart of binary to ASCII. In case of binary to ASCII, we are adding 30 or we are adding 37 hexadecimal. While converting the ASCII number into the binary, we will be subtracting 30 or we will be subtracting 37 to get the binary number corresponding to the ASCII code. So as we are doing addition process in binary to ASCII conversion, we will be doing subtraction process while doing the ASCII to binary conversion. So first of all, the pointer is being initialized in the HL pair where the ASCII number is being stored in the form of an input. In the previous example, binary number was the input and the ASCII code was the output. In this case, ASCII code is the input and binary will be the output. So first of all, where the ASCII is stored, we load that into the memory pointer into the HL pair, and D pair will be pointing where the result will be stored in the form of a binary. And then we have to use a counter. Now something went wrong. Here it should be C. Just wait. So C register will be used as a counter. So with this, we are starting with, first of all, we have to get the first data which is required to be converted. Now this data is in the ASCII code and it is copied into the accumulator. Once it is copied into the accumulator, then we are in requirement of a certain set of the statements or the instructions which will be converting it into the binary. And so for that, we have written a subroutine. So it is going to call a subroutine named as binary. So instead of executing the next, it will jump to call binary. It will call binary subroutine. So binary subroutine is written over here. What this binary subroutine is, first of all, it is subtracting 30 from the number. Once we are subtracting 30, then we have to check that after subtracting 30, whether the number is less than 9 or it is more than 9. And for that, we will be using an instruction CPI 0A. If there is a CPI 0A, and if the number after the subtraction with 30 is subtracted, if it is less than 9, and then it is compared with 10, so naturally carry will be generated. But if it is more than 10, then carry will not be generated. So here we are using return on carry, means conditional return instruction, which will be showing that whether the number is less than 9 or more than 9. If the number is less than 9, carry will be generated, so it will return. But if the number is more than 9, then carry will not be generated, so it will not return. So what it will do, it will again subtract 0.7. Because you know that if the number is in between 0 to 9, we are adding only 30. So if the number is in between 0 to 9, we will subtract only 30. But if the number is more than 9, then instead of subtracting 30, we have to subtract 7 more. So that is why if carry is not generated, it means the accumulator content is more than 9. And then for that, we are again subtracting 0.7. If not carry generated, then subtract 7 to find the number in between A and F. And then it is going to return. And whenever it is going to return, it is coming over here. That is Stxd. What this will be doing, it will be storing the content of accumulator into the memory, which memory whose address is present in the D pair. And then we increment the content of D. After incrementing the content of D, we are incrementing the content of H, and then we are decrementing, the counter. Then we are decrementing the counter, and this process will be repeated till the counter has become 0. Once the counter will become 0, it will not go. Otherwise, the counter is not 0, it will go back, and in back, it will take the data to be converted. Once the data is taken again, it will call the binary where 30 is subtracted first, then it is checked. If number is less than 9, it will return. Otherwise, it will again subtract, and it will return the final value in the form of a alphabet to the memory location by the instruction Stxd. And then it is going to increment the content of D, increment the memory pointer, and then it is going back again, where the next data byte is being taken, is read and stored in the accumulator. And after that, it will go onwards. So the important thing which is related with this is if, as I told you, that if the number is lying between 0 to 9, then the 30 and 39 will be the ASCII code. If it is A to Z, 41 to 5A. So it means we are adding 30 or 37 depending upon the value which is required to be converted into ASCII. Similarly, we are subtracting the 30 if we want to convert the ASCII number into its binary or the decimal equivalent. And if the number is more than 9, we will subtract 37. So the way we are adding the values to convert the binary number into the ASCII code, similarly, we are subtracting the value 30 or 37, depending upon the number which has to be converted from the ASCII to the binary. And this process will be repeated till all the numbers are being converted. So this is the program for the second code conversion program, which is from binary to ASCII and ASCII to binary. Now the next part is the BCD arithmetic. We have studied BCD numbers. What is the BCD number from 0 to 9? And in most of the cases, it is required, since if we are working with BCD, we must know how to add two BCD number, because we know the maximum binary number which we can represent the maximum BCD value, that is 9. It is 1001. More than 1001 we cannot represent for the BCD, because BCD is restricted up to 9. So if it is 1100, it is not, it is remain unused. So how to represent that? So for that, let us go with the detailed arithmetic related with the BCD addition. The addition of two BCD number, how it can be done. So there may be three cases, and we have to study these three cases. First of all, whenever we add two BCD number, it may be possible that the sum is equals to 9 or less than 9 with no carry. So if it is so, for example, if we take 6 and 3 as the BCD number, so 6 binary number is this one, 3 binary number is this one, and it is a BCD of 6, BCD of 3. So when we add, we will be getting 1001. So this is the normal addition case. So this addition is carried out as in the normal binary addition is being done, and sum is 1011, 101, 1001, which is the BCD code for the 9. So there is no problem if we are adding two BCD number and the value is less than 9 or 9 without any carry. But the second case is if the sum is greater than 9 and there is no carry, then what will happen? Suppose we are adding two BCD, BCD 6 and BCD 8. So convert binary coded decimal of 6, that is 0110, BCD of 8, that is 1001. And whenever it is going to be added, it will become 1110. No carry is generated. But of course, this value, this BCD value is more than 9, which cannot be represented in a BCD. So if the sum is more than, so it is an invalid BCD number. And this is because sum of the two digits is going to exceed 9. That is why it is an invalid. So whenever this type of thing occurs, the sum has to be corrected. And this has to be corrected by adding decimal 6 in valid BCD numbers. How? By adding decimal 6, that is 0110. So we have got, after addition of 0 and 6, we have got 1110. And so we will be adding decimal 6 into that, that is 0110. So what we are getting, this is 0, this is 110, this is 111, and this is 110, and one carry is generated. So this will be representing 1, and this will be representing 4. Now this is the correct BCD form of this. This is an invalid form, but this is a valid form. And to make the form valid, that is why we are going to add decimal 6 into that. So after addition of decimal 6 in the lower level, carry is going to be produced into the second decimal position, and it is considered as a most significant bit of that. So that's all from today. Rest of the